So, hello everyone again. This is lecture 5 part 1 of ray optics and optical instruments. This may be the last lecture of this lecture series. So, in the last lecture we started with the last topic, that is optical instruments, in which we studied about microscope. So, basically there were 3 types in which the images were being formed near at infinity, at some object u, and at infinity. So, one was at near point, one was at infinity, one was at near object u. So, after that discussion we will go on with the microscope, followed by summary, and that will be your end of ray optics and optical instruments. So, first of all let me go to the course outline and then I will start the discussion further. So, I am Sameer Lavankar. Let us begin our discussion. Okay, so course outline for you first of all. So, we started with the introduction, in which we understood the basic concept of ray optics, that is discrete particle theory of light, in which we understood every particle, the complete light is in the series of discrete particles. These are spot particles which are aligned in a single line. Okay. Then there were two major topics. So, first point was that light always travels in a straight line, which is 3 into 10 to the power 8 meter per second, and the second point was that light always travels in a straight line. Okay. So, after this introduction part we went on to the reflection of light by spherical mirrors. In the reflection of light by spherical mirrors we understood first of all the basic definitions such as principal axis, pole of the mirror, then focus, what is focus basically. Then we understood the concept of two laws of reflection. The first law of reflection states that the angle of incidence is equal to the angle of reflection. The second point states that the angle incidence ray, the normal ray, and the reflected ray all lies in the same plane. Then after the reflection of light was being completed, we went on to the refraction concept. What is refraction? Refraction is basically a phenomena which is happening or which occurs in light, which is related to bending up of light or ray of light on passing from one medium to another. It has to be make sure that if the medium is being passed from one point to another, there is a difference in the optical density, or we can say there is a difference in the refractive index of the both media. One media is denser, one media is rarer. Okay. So, either the ray of light can bend towards the normal or away from the normal. So, after this basic concept of refraction, we went on to the two laws of refraction. The first law states that the incident ray, the normal ray, and the refracted ray all lies in the same plane, as similar to the reflection. The second was called as the Snell's law of refraction, which says that the ratio of the sine of the angle of incidence to the sine of the angle of refraction is constant, which is equal to the refractive index of medium 2 with respect to medium 1. Okay. So, after this third point was completed, we went to the fourth point, that is total internal reflection. In total internal reflection, we first of all understood the concept that this only occurs when the ray of light is being passed from a denser medium to a rarer medium. So, when the passage is being done, then at the interface the ray of light goes or bends away from the normal. So, at a particular angle of incidence, there is a point at which the angle of refraction is equal to 90 degrees. That particular angle of incidence is called as critical angle. If we go on further with the increase in the angle of incidence, we go through an angle of incidence I, which is greater than this critical angle denoted by IC, then we get the total internal reflection. What does total internal reflection mean? As the name suggests, the complete ray of light goes inside the same medium only, there is no refraction happening, hence the complete intensity or majority of the intensity is being intact. So, this is the complete concept of total internal reflection. Also, we studied that there are three examples of total internal reflection. The first was based on optical fibers, and another was basically a light lamp which we observe in our day to day appliances. Basically, it is visible in your surroundings also. You can buy it in your shops. Okay. So, this was about fourth point. Then moving on to the fifth point, that is reflection at spherical surfaces and by lenses. So, now after this point we basically went on to the complete applications of your rules of reflection, laws of reflection. So, basically to find out the image, we understood the complete lens equation, the mirror equation, that is 1 by u plus 1 by v plus 1 by f, the complete derivation was being done, and finally the actual image, the practical image was being observed using 2-3 examples. So, first example was that first of all the assumption was that we always assume paraxial rays such that sin theta is approximately equal to tan theta is approximately equal to theta. Then the parallel rays are being going to the focus, then any light which goes through the pole gets angle of incidence equal to angle of refraction, and any light which goes through the focus comes out as parallel to the principal axis. Okay. So, these all things were understood in the fifth point. Then the sixth point, in the refraction through a prism. Before refraction, we also went to refraction of thin prisms. So, similarly, we, as the analogy for reflection was being done, refraction was also being done, just the complete part was being denoted at this side. Also in this we also understood the concept of Lenz-Maker's equation and the Lenz-Maker's equation and the Lenz equation, that is 1 by u minus 1 by v is equal to 1 by f, and similarly 1 by f is equal to n21 minus 1 into 1 by r1 minus 1 by r2. These was the Lenz equation and Lenz-Maker's equation respectively. Then in refraction through a prism we understood the concept of two different refraction happening on the same different angles. So, one was angle of incidence, one was angle of emergence, in the medium both r1 and r2, and we got the formula for this angle of prism, the relation between angle of prism, angle of incidence, angle of refraction, emergence, or here in this case. Okay, then finally after refraction through a prism, right now we are in optical instruments, in which we understood first of all the concept of microscope. So, there were three different ways in which the image can be formed. Today I will just go on with a little revision of that, and then we can move on to the final concept, that is telescope. Okay. So, let us start our today's discussion now. So, optical instruments. So, these all things were already been explained in the previous lectures only. Okay, so there were three cases basically. One was eye focus on near point, one was near the infinity, and one was near the when the object is at distance u. Fine. So, for the first one, when the image is formed, as you can see, when the image is formed at near point D, then the magnification is equal to 1 plus capital D by f. What is capital D? Capital D is the distance, that is 25 centimeters here, and f is the focal length. Fine. So, this thing has been completed. Then for the next point, that if the image is at infinity, as you can see, if the image is at infinity, then we can find out the angular magnification, which is equal to tan theta naught, which is equal to small h by capital D, which is approximately equal to theta naught. Okay. This thing has also been explained. Moving on to the third point, when the object is at u, where it is written, yes. So, then the image when the object is at u. So, for this also we do the angle of angular magnification only, and that angular magnification is equal to capital D by f. So, these are the things which you need to remember for the microscope concept. So, basically for the image which was at near point, the magnification was 1 by D by f, and you just, if you subtract minus 1 from this, then you will get the magnification for the object when it is at distance u, when the image formed when the object is at u. Okay, fine. So, that is the end of your microscope. Let us move on to the new discussion of telescope today. So, let me start the telescope discussion. So, these all things were also been explained, that is compound microscope. So, compound microscope. So, basically the normal simple microscope can have a intense magnification, maximum magnification of less than or equal to 9 only, but a compound microscope can have a magnification greater than that. So, basically you can even get a magnification of 250 also. So, these all things for the final discussion of the previous lecture. Let us today start with the telescope concept now. Okay. So, the telescope is used to provide the angular magnification of distant objects, quite evident. So, basically you just need to remember first of all what is microscope used for. So, there is something called as microscope, there is something called as telescope. Fine. So, microscope is used. So, basically we have to see things called as microorganisms. I am just putting an example here, right. So, basically they are in itself tiny particles, and we try to magnify them, right. So, this is the basic application of your microscope. What is a telescope? Telescopes are basically used to find out or to view let me write it, view planets, moon, stars, etc. So, basically to view constellations, to view sky, basically we use telescope. So, what does it do? It magnifies the large objects which are already, those things are already large, but they are at a very far distance from us. So, basically these are for very far distance from us, and this is very near to us, but their what we can say, their size is very small. So, here size is small, but so we use for magnifying, and here size is already big, but it is very far, size is big. Okay, fine. Let us move on. So, now the telescope is used to provide angular magnification of distant objects. So, what does it do? It provides angular magnification here. Okay, how does it provide? I will try to explain you in the subsequent points. So it also has an objective and an eyepiece. So similar to the compound microscope, it also has an eyepiece, as you can see, and it also has an objective. So basically these are nothing but the denotions of a convex lens being used for the complete magnification concept. Okay, so it also has an objective and an eyepiece, fine. Okay. Next is, but here the objective has a large focal length and a much larger aperture than the eyepiece. So as you can see that the focal length is also greater for this. So if I write it as f1, if I write it as f2, then the larger focal length is of objective. That means f1 is greater than f2 and much larger aperture. Aperture, so you can directly see the aperture is higher for objective than eyepiece. Fine. So this thing has also been explained, but here the objective is a larger focal length and a much larger aperture than the eyepiece. Light from a distant object enters the objective. So as you can see, the light is being entering from this portion here, it is entering from a very far off position. So this light is basically the light from the planets, stars, etc. So light from a distant object enters the objective and a real image is formed in the tube at its second focal point. So basically the image is formed at second focal point here, as you can see it is formed here, fine. So this thing has been explained again here. The eyepiece magnifies this image, producing a final inverted image. So basically after the inversion is being done, the final image is formed, which is much more highly magnified than the original image being formed here. This image is due to the first lens, that is objective, and then what does eyepiece do? Eyepiece tries to magnify it much more, fine. So the eyepiece magnifies this image, producing a final inverted image. The magnifying power m is the ratio of the angle beta subtended at the eye by the final image to the angle alpha which the object subtends at the lens or the eye. So basically it is a simple theory or simple definition of magnification only, just angles are being changed due to so as to correspond it to the microscope concept here, fine. So the magnifying power m is the ratio of the angle beta subtended at the eye by the final image to the angle alpha. So basically this is your angle beta here, that is subtended by the angle by eye at the eyepiece pole position, and basically angle alpha is that this, what does this object subtends, okay. So this thing has been explained. So this is the angle for the final image portion, and this is the which object subtends. So therefore at the lens or the eye. So basically magnifying power m is the ratio of the angle beta subtended at the eye by the final image to the angle alpha by which the object subtends at the lens. As you can see, it is at the lens only, at the lens or the eye, fine. Hence m is equal to approximately equal to beta by alpha, which is approximately equal to h by fe into f naught by h. So how does is this thing obtained? So as you can see, what is beta here? Beta is this portion here. So beta, as you can see, is this is also fe for you. So you can write it as tan beta is equal to h upon fe, and similarly you can write tan alpha. So I am using this triangle first of all for tan beta here, and then similarly I am using tan alpha, I am using this triangle here, that is this one, fine. So this will be nothing but your again h by f naught, fine. So this is f naught. Now from the basic concepts of your microscope and all, we understood that tan theta is approximately equal to theta. Therefore we can write beta is equal to h upon fe and alpha is equal to h upon f naught. Therefore we can write it as beta by alpha is equal to h by fe divided by h by f naught. So h gets cancelled, therefore we get f naught by fe, hence which this is the magnification. So magnification can be obtained directly for a telescope if you just know the focal lengths of your objective and the eyepiece. So this is the simple concepts of your telescope. Let us move on. So in this case, the length of the telescope tube is f naught plus fe, quite evident, as you can see. For this is the total tube length, that is f naught plus fe. You just need to remember these all things, because this can be asked that what is the tube length for your telescope, what is the tube length for your microscope, and so on. So here in this case, the length of the telescope tube is f naught plus fe. Terrestrial telescopes have in addition a pair of inverting lenses to make the final images erect. So these are just the now the application parts of different types of telescope which are being available in the market. So terrestrial, there are something called terrestrial telescopes, they have in addition a pair of inverting lenses to make the final image erect. So there is one more lens being used here. What does it do? It just inverts the image. So inverting an inverted image gives you a erect image. because as you can see the final image is in form which is inverted here. So, if you use one more lens here, then that can be used to make the inverted image an erect image. Fine. Okay. Next. So, refracting telescopes can be used both for terrestrial and astronomical observation. So, what does a terrestrial telescope do? As the name is terrestrial. So, basically it is used to find out far off let us say animals or far off any insects and so on for using a telescope, and astronomical as the name says astronomy. So, basically it is related to stars, moons, etc. Okay. Next, for example, consider a telescope whose objective has a focal length of 100 centimeters and eyepiece a focal length of 1 centimeter. So, as you can see the focal length of objective is given, that means this value is given to you as 100, and focal length of eyepiece. So, basically this value is given to you as 1 centimeters. Question asks is what is the magnifying power. So, magnifying power of this telescope is m is equal to f naught by fe, which is equal to 100 by 1, which is equal to 100. What does it mean? Basically the magnification of that object is done 100 times. That means let us suppose the average size of that thing is 1 centimeter, then you can at least view that as a 100 centimeter size thing. Fine, let us move on then. So, next is let us consider a pair of stars of actual separation 1 degrees. So, please remember this magnification is angular magnification, this is not a linear magnification. Therefore, you cannot directly use h dash by h is equal to m here. Okay, so let us consider a pair of stars of actual separation 1 minutes, that is 1 minute of arc. The stars appear as though they are separated by an angle of 100 into 1, that is 100 minutes, that is 1.67 degrees. So, basically what does it happen? The magnification is such that we view that stars as in they are separated by 1.67 degree angle, as in the initial portion they are separated by 1 minute difference only. Okay. So, this is just the application, this is just the application part. You just need to understand what is the actual meaning of magnification here. This example has been explained here. So, basically let us consider a pair of stars. So, basically actual separation of 1 minute, but on viewing it through a telescope the actual separation changed to this apparent separation as 100 minutes, which is also equal to 1.67 degrees. Okay. The main consideration with an astronomical telescope are its light gathering power and its resolution or resolving power. Quite evident, because as the things are very far, you just need a good sharp image, a good resolved image of those planets, moons, because sometimes these telescopes are even used to find out the craters on the moon, etc. So, the resolving power should be very strong for these astronomical telescopes. The former clearly depends on the area of the object. So, this is just the theoretical part, that what does it depend upon? It depends upon the area of the object. Okay, fine. Let us move on. So, with large diameters fainter objects can be observed, quite evident. So, as you keep on increasing the diameter, the resolving power of the telescope increases. As the resolving power of the telescope increases, the objects which have blurry vision in the previous smaller diameters can be observed much more clearly. Fine. So, this thing has also been explained. The resolving power or the ability to observe two objects distinctly which are in very nearly the same direction also depends on diameter of the object. So, basically what is resolving power? As I said that sometimes the separation is very less. So, that separation due to its very less portion and very far distance from the actual microscope, sometimes those things cannot be distinctively observed. But if the resolving power is very much higher, then even that slightest disturbance or slightest difference in the position of those can be viewed much more clearly if the resolving power of the telescope is very high. So, this is the basic agenda, or this is the basic definition of resolving power. So, the resolving power or the ability to observe two objects distinctly which are in very nearly the same direction also depends upon the diameter of the objective. So, the desirable aim in optical telescopes is to make them with the objective larger diameter. So, basically what do we do? The basic aim for making any telescope is we just try to increase the diameter as much as we can, not even very high, but at optimum diameter such that our work can be completed very clearly. Okay. Next is so now again this is the complete explanation part is over. Now only the few examples are being explained here. Okay. So, the largest lens objective in use has a diameter of 40 inches, that is 1 meter. So, 1 meter diameter is being used for a telescope. So, objective, as you can understand, for this is that lens objective focal length being explained here. So, the diameter of this objective is 1.02 meters. It is at the Yerkes Observatory in Wisconsin, USA. Such big lenses tend to be very heavy, quite evident as the diameter is very high, and therefore difficult to make and support by their edges. Further, it is rather difficult and expensive to make such large size lenses which form images that are free from any kind of chromatic aberrations and distortions. Fine. For these reasons, modern telescopes use a concave mirror rather than a lens for the objective. So, right now when the recent telescopes does not use a convex lens, they use a concave mirror. The application or the detailed part is not required for a 12th class syllabus. For now, you just need to understand that for major aberrations part. So, just to cut short the aberrations to make the resolution power much more higher, nowadays concave mirrors are being used. So, for these reasons, modern telescopes use a concave mirror rather than a lens for the objective. Telescopes with mirror objectives are called a reflecting telescopes. So, you can just remember this, that what are these reflecting telescopes, that is telescope with mirror objective. So, basically if a mirror is being used in the place of these lenses, then that telescopes or that part of that division of telescopes are called as reflecting telescopes. Fine. There is no chromatic aberration in a mirror. So, what is this chromatic aberration? You just don't need to remember now. You can understand this chromatic aberration as errors which happen in a what we can say telescopes, or the positions of the image being formed after the light enters through the objective, through the eyepiece and so on. Fine. So, this is also being done. Let us move on. So, mechanical support is much less of a problem since a mirror weight much less, quite evident. So, transportation is also very easy. Then a lens of equivalent optical quality and can be supported over its entire back surface, not just over its rim. So, basically this is one of the example of how a secondary mirror is being used. So, objective is okay, but a secondary mirror is being utilized here, and hence this is the application of usability of a mirror in a telescope. Fine. Next thing is, so now one obvious problem with a reflecting telescope is that the objective mirror focuses light inside a telescopic tube. So, this is everything is being interacted at the center portion here. So, therefore, one must have an eyepiece and the observer right there obstructing some light depending on the size of the observer cage. This is what is done in very large, approximately 5.08 meters diameter Mount Palomar telescope, California. The viewer sits near the focal point of the mirror in a small cage. Another solution to the problem is to deflect the light being focused by another mirror. So, this is that Mount Palomar telescope being explained. As you can see, such large diameter telescopes are being observed. This is in California. Okay, fine. So, let me stop it here only. I will convey the last slide of this in the next part, and then I will go on with the summary, and that will be the end of your ray optics. So, let me stop it here only. Thank you so much.